So good morning, everyone. So my name is Naila and I work at Naver Labs Europe, which is the European research lab of Naver. So for those of you who aren't aware, Naver is it's a South Korean company which is quite dominant in internet search. And we have many other services like maps, blogging services, messaging services as well. So we're really quite a big company in Naver in Korea. And about a year and a half ago, Naver bought a research lab in Grenoble, which has become Naver Labs Europe. And so there we do work on computer vision, as you'll see, and then also a lot of other areas in machine learning, for example, in NLP, in search and recommendations, and other topics. So with that, let me start the topic of the talk. So today, as I said, I'll discuss in the recent past on predicting aesthetic properties of images. So what we're interested in is really data-driven approaches to aesthetic prediction. And we're interested in this because data-driven approaches have been quite successful for a large number of topics related to computer vision. So for example, in particular things that address what we might consider to be fairly objective properties of images. By objective, I mean things that if you asked 10 people's opinion on something about an image, they would pretty much all agree, right? So for example, if you had an image of a dog, most people would be able to say that this is a dog unless the image is particularly degraded or there's something especially wrong with it. So for example, the topic of object recognition is what I just described, and that's for those of you who might be aware of the ImageNet, the large-scale challenge related to ImageNet, that is the task that's being addressed there. Also, there are topics related to semantic segmentation. So that's a problem where if you're given an image, you'd like to know what semantic category is given for every pixel. So you might see a pixel and you say, okay, this pixel corresponds to grass, this corresponds to sky. That's the problem of semantic segmentation. Once again, very objective type of problem for a human. Once again, also very well addressed with machine learning-based techniques. Also things like local feature matching, and you can think of many more examples of this. So as I said, they're quite successfully tackled using this type of data-driven machine learning-based approach. So what we really wanted to answer in this stream of work is, can we have the same type of approach for, let's say, image properties that are less objective, right? In particular, aesthetic appreciation and visual aesthetics. So to address this problem, we needed two ingredients, the same ingredients that you would expect for any sort of data-driven approach. That is having an annotated data set, because I'm speaking about really supervised learning here, and also effective representations of your data, in this case of images. So for a global outline, I'm going to talk to you about these two aspects. The first is a data set that we collected for this task. So really starting from the beginning of any sort of machine learning task or supervised machine learning task, how do you collect the data you need? And next we'll describe, okay, how do I use this data to train a model for unified aesthetic prediction, and I'll describe later on what I mean by unified. So starting with the first. So we want to solve this problem of aesthetic prediction. What is that exactly? So in the computer vision community, when we talk about aesthetic prediction, we tend to be talking about three typical tasks. So either you might have a binary classification task where you will say, okay, given an image, for example, some of these images here, you'd like to be able to say, answer a simple question. Is this sort of like a high quality image or is it not? You might also tell yourself, okay, like saying that an image is good or bad is a bit, it seems like a bit of a hard decision. It's a bit maybe arbitrary, especially at the boundaries, right? How do you determine where you move from good to bad, right? So rather than do that, you might like to give a score. You might like to say, okay, from a scale of 1 to 10, how nice is this image, for example? And you might want to go even further than that. So you might say, okay, do I want to reduce, let's say, the opinion about this image to a single number? Maybe I'd like to have a range of scores to have some sense of the diversity of opinion that you might have for an image, right? And in that case, you might like to determine like a score distribution. So to tackle any of these problems, which could be like a categorization problem, a regression problem, a structured prediction problem, the pipeline is fairly similar, right? So across the history of works in this field, most, they tend to be tackled in the following way. how many of you guys are fairly familiar with computer vision, at least supervised, like object recognition type of problems? Okay, like pretty much most of you, so that's good. So then this should be familiar to you. So you're giving some kind of visual content. Like let's say you have an image, you extract features. So most of you guys, it seems to be familiar with things like SIFT, for example. And then you use these features, you aggregate them some way, for example, and you apply them, you input them to some sort of prediction model, and you get whatever target output you're interested in, right? Whatever prediction, be it a class or a score or a distribution. So for this task, the types of features that have been used in the past have been things like, handcrafting things just to determine the aesthetics of an image. So you might ask yourself, okay, if I wanted to know if an image is like high quality or low, I would consider things like blur, like contrast, saturation of colors, composition of the image, things like this. So there have been a lot of features in the past that have been really designed to capture these properties. More recently, it was shown that more generic image features, so things, for example, like SIFT, perform actually equally as well for this task. So there's not really a need to sort of handcraft these, what you might consider to be aesthetic properties. And this tended to work fairly well. Of course, more recently, so deep models have kind of superseded those, where you sort of kind of combine the image representation portion of the model and the prediction model into one single model that can be trained end to end. And so this is the type of architectures we tend to deal with. So as I mentioned, aesthetic appreciation is a subjective property, right? So there's no right answer to any of the sort of questions we asked before, right? So what people tend to want to answer is something like, what would be a consensus opinion? So something like, how would most people label this image? How would most people score this image? So given that we're asking this type of question, we really need to have a fairly robust idea of most people, right? So this means we need large-scale data for this in two main aspects. So number one, we need quite a few images to be able to train a model of this type. And we also need, most importantly, or let's say very importantly, a large number of annotations per image. So for this type of task, it's not sufficient to say, I'm going to ask 5 people what they think, and then I'm going to sort of aggregate that, those opinions. We need to have like a more large-scale set of opinions than that. So given those requirements, how can we capture this type? How do we get this type of annotations we need to train our models? So what people typically do is they sort of crawl websites that have annotations and images that are sort of relevant for this task. So one possibility is Flickr. So I guess most of you or all of you guys are familiar with Flickr, which is like a website that's free to use, and people upload pictures for many different purposes, right? So it could be people who are professionals who sort of want to show their work. It could also be people just sharing family vacation photos. It's completely free, and you can rate these photos. The drawbacks of this is that the photos, the ratings don't necessarily correspond to whether the images are nice or not. They might simply be friends tagging or liking photos that their friends put up for different reasons, right? So there's not really like a clear linkage between what we want to know and what these ratings correspond to. So perhaps something a bit more relevant is photo.net. So this is a community of photography enthusiasts. So these tend to be more like serious hobbyists, serious photography amateurs. Like let's say amateurs, hobbyists, and also quite a few professionals as well. And once again, on this website, users can score other people's images. However, in this case, the scoring is really supposed to be meant to depict, to let the photographer know how good their technique is, basically, how good their pictures are. And then a third example of this is a website called dpchallenge.com. This is it's a similar community to photo.net. The kind of unique nature of DP Challenge is that, as the name suggests, the community is organized around challenges. This means that every week or every couple of weeks, a challenge is organized, which is sort of aimed to push people's skills in a specific expertise related to photography. And I'll show you an example of that in a second. The nice thing about this website, this last one, is that there's a very large community, and it's also very much geared towards improving people's photography skills. So the scores that are given are quite robust and really very relevant to what we want to study. So I'm going to dig into, so I'm just going to show you an example, as I mentioned, of a type of like an example challenge in dpchallenge.com. So here, this is a challenge titled Skyscape. The description is make the sky the subject of your photo this week. And so what would happen is that for a week while that challenge is ongoing, people would submit their photos. Other people in the community would rate them. And at the end, the images are scored by are ranked by their mean score. And if you're lucky, if you're very good, you might even get a ribbon. And so this community takes this sort of stuff quite seriously. So here is the data set that we collected for this challenge. So this data set was collected from images and associated metadata from dbchallenge.com. So just at a glance, it's fairly large scale, especially for this type of problem with more than 250,000 images, which are associated with almost 1,000 different challenges. The nice thing about this, and really the main advantage of this data set, is that there are really quite a good number of votes per image. So on average, every image has about 200 votes. Also, the data comes with semantic annotations, but they're fairly weak. So this is in the form of tags that a photographer gives to an image. So when someone uploads an image to the website, they're allowed to tag the image with up to 2 tags. But they're not required to. So many images don't have any. Some have 1, some have 2. And also, these tags are not free-form, so they're required to select them from a list of tags. So this is a bit weak in the sense that there are likely to be many false negatives because there are many tags that are just not present, that are relevant. And then another issue is that because it's not really, the users are allowed to choose whichever tags they want. So if someone interprets a tag differently, then the tags can be quite inconsistently used. So this is another issue with using these tags. There are also a few style annotations that are associated with these images as well. And also there's quite a lot of textual comments because one other aspect of the community is that when you upload a photo, you're really encouraged, like other members are encouraged to sort of critique it, give constructive feedback, tell them things that work, tell them things that didn't work. So that actually is quite useful information as well. So to take a deeper look into the data we're dealing with, so this is what I'm showing you here is a histogram of the mean scores given to the images in the data set. So you can see that there's like a huge bias, right? Most images are sort of like average, you would say. And as you'll see later in the talk, this will cause all kinds of problems, but it's really, it's a hard nut to crack this one because as you would imagine, most images are not going to be on the extremes, right? They're not going to be super bad or super good. They'll be somewhere in between. It's a similar case for if you look at the tags that people give to these images. Once again, you see that there's not just a bias towards sort of average quality, although average quality is maybe not what you and I would consider average. These guys are very, they're very rigorous. But then also there's a bias in terms of the content. So you see a lot of the images relate to things related to nature. So there are a lot of landscape photos. There's a lot of animal photos, portraits. And then there's kind of a long tail of other types of content. And then, so these are some examples of the tags that I mentioned to you. These sort of this limited list of tags that people can use. And you can see that it's also a bit mixed, right? So not everything is semantic. So you have things like, like as I said, like architecture, portrait, but then you also have tags like humorous, which is a very abstract concept. So there's quite a mixed bag there. So what I'm showing you now is basically some prototypical score distributions that are associated with every image. So as I mentioned, every image tends to have about 200 scores on average. So these are scores from 1 to 10. So basically you can give an image a score from 1 to 10. And then if you plot the histogram of those scores, you tend to get things like this. So the vast majority of images have distributions kind of like this. So you see most people kind of rated like a 5.5, like somewhere in the midpoint of the rating scale. And then you tend to have a few images which might have a rating more like this. So they're really bad as rated by people, or pretty good. Like most people consider them to be quite good, right? But these images are quite rare. So what we wanted to do also is to have to kind of quantify these intuitions. So what we did was we've tried to fit different types of probability distribution, so distribution functions, to these score distributions to get a sense of what tends to fit best. We tried different things, but as you can kind of see yourself, normal distribution, the Gaussian function tends to work pretty well for most images. And then there are a few cases yeah, like these, where, you know, a Gaussian function is not going to work really well, but like a gamma function tends to work quite well. Yeah, and this is just quantifying that. So you can see if you look at the root mean squared error scores for these fits, you can see that in general the Gaussian function works pretty well. But then if you have a really low score, really high mean score, the gamma function does better. So that's it for the first part. So now you have an idea of the type of data we're working with. Now I'm going to describe how we use it to train our deep architecture for unified aesthetic prediction. So why do I say unified? So let's go back to some of the prediction problems we were discussing in the beginning, right? So as I mentioned, we tend to look at three types of problems, either like a binary classification problem or a mean score regression problem, or like a structure prediction problem where you want to predict a distribution of scores. But how would we get these annotations? So if you're dealing with a data set like AVA, which is a typical type of the typical type of data set that is used, you actually derive like your other types of annotations from your raw scores, right? So really you have a set of scores, you have a distribution, and then you would usually compute the mean score given this set of scores that you have. And then if you want to do binary classification, you just simply threshold it, right? So you say, okay, anything above 5.5 is high quality, anything below that is not. So what we try to tackle in this work is rather than sort of use these derivative problems, let's just stick to the original task. Let's try to predict a score distribution, and from that we can solve any of the other ones, right? Just by deriving the annotations or the predictions from the distribution. Yeah.
Do you choose the threshold in order to have a balanced data set? Or?
No, so we chose this threshold. It's kind of hard because you can have a balanced data set, good or bad, but what we don't really like about doing this threshold is that no matter where you do, like no matter where you put it, it's just going to be this boundary that's completely ambiguous, right? So anything slightly to one side is just switches the label for no real reason. And so for that reason, we prefer to stick with just using the score distributions themselves. Yeah, so this for us is a problem that's it's not the ideal problem, I would say, to solve. So why do we care about computing score distributions themselves? So even though most works do try to solve a classification task, not only is this, as I said, a bit arbitrary in where you put the boundary, but then also it kind of erases some of the information you might have in the distribution, right? So to give an example, if you take a look at these two images, they both have the same mean score. They would both be rated high quality. But if you look at the score distributions, you can see that there's a fair bit of divergence of opinion in the second image, and that would be like an interesting thing to capture, right? So a distribution has more than just the mean. It's a bit, it's kind of, it doesn't capture the full scope of information you have there. So we really like to keep that when we're solving our aesthetic prediction task. So we're not the first people to look at this. So there's been previous works on how to predict aesthetic score distributions. So what people have focused on in the past were, for example, trying to get rid of unreliable annotators. So let's say you have people who kind of rate images somewhat, let's say, inconsistently. How can we detect and remove those types of annotators? That's one kind of thing that was tackled. Another problem people try to tackle is how do we deal with the different types of imbalance and bias that I mentioned in the data set, right? So for example, some people used row weighting schemes to sort of give more weight to rarer examples in the data sets and vice versa. So what we tried to focus on was how to actually leverage semantic information while training our model for this prediction task. So why do we care about leveraging semantic information? The reason why is because we know that aesthetics is dependent on the content in your image, right? So given a different image, what makes it aesthetically pleasing is going to be different. So to illustrate this, I'm showing here examples of high quality images, so images that are rated very highly by people in the AVA data set for three different types of semantic content, right? So I'm showing you some architecture, let's say, different types of animals, and then flowers. And you can see that what makes these images aesthetically pleasing is quite different, right? There's really a type of style that tends to be associated with a certain type of content. So for example, if you have architecture, very often you have like high dynamic range images. There's also a lot of play around like vanishing points, leading lines, things like this. Whereas for animals, it tends to be very highly saturated. Also, there's a lot of sharp focus on the foreground, a bit of blur in the background sometimes. And then for flowers, very often they like, you know, this kind of sharp contrast with the background is appreciated. So you can see that what makes an image nice is definitely dependent on the content that's within it, right? Which I guess is pretty intuitive. So the one issue with trying to leverage semantic content is that, as I mentioned before, the AVA dataset doesn't have very robust semantic annotations, right? So we have, as I mentioned, these tags that may or may not be given to an image. But as I said, they're quite incomplete because there'll be many false negatives. So it's difficult to use this type of information. So what different works have tried to do is to try to get like pseudo labels, for example. So one thing you can do is you can say, okay, I'm going to take all my images in AVA, I'll cluster them, and then I hope that these clusters are kind of semantically coherent. And then I'll kind of use these clusters as, let's say, as categorical IDs. That's one thing you can do. Another thing that's been done is to try to extract features from some auxiliary network, for example, and then kind of add these features, like kind of plug these features into your network at some point to sort of inject, let's say, semantic information when you're training your network, right, as some additional features. That's another thing that you can do and has been done. So we tried a different approach to this, which was inspired by model distillation. So for those of you who may not be aware, in a nutshell, what model distillation is trying to do is to say, take a network, you can call it a teacher network that's already been trained for some task and does that task quite well, and then use that task, that teacher network, to supervise another network, which you can call like the student network, okay? So usually in order to do this, what, you know, the original formulation, what it did, is it took, for example, it took a classification model trained to output softmax probabilities for a set of classes. It used these output softmax probabilities as the target for the student to learn, right? So now the student is not being trained with the ground truth labels. The student is being trained to replicate the output of the teacher, okay? So this was conceived for network compression originally. The idea was to say that typically your teacher network, it does a really good job, but it's quite huge and might not be efficient for your purposes. So what you like to do is to train a student network that's more efficient, but that it can also replicate fairly well the teacher results, okay? In our case, we use it for a somewhat different motivation. So in our case, what we like to do is to use this teacher network to provide us with some sort of pseudo ground truth for the semantic properties of our images, right? So to do this, we say we take the AVA images, we compute the softmax probabilities for those images, and then we use those softmax probabilities as some sort of semantic signature for those images. And what we hope is with this, so once we train our network for this task, what we're hoping is that the weights of the network have a bias towards more semantically meaningful information, and that will give us a better initialization for our final end goal. So in more details, as I mentioned, so to start off with, in order to get these softmax probabilities, we take all the images in AVA, we run it through like a very good classifier, right? Deep classifier, in this case, ResNet. And then we use this to output, to give us a set of softmax probabilities for each of these images, right? So we have a set of images, and we have a set of associated softmax probabilities. And this is what we call our semantic signature. Once we have that, we take our network that were designed for static prediction. So I won't get into the details of the architecture design, but basically what it tries to do is to capture a bit more, particularly resolution, a bit more spatial information about the images. Because of course you would imagine that having more fine-grained spatial information would be helpful to determine the aesthetic properties of an image. Then we take this network, and then we train it to predict those softmax probabilities, right? So the target of the network now is to predict the semantic signature. And lastly, we take this network that we just trained for this task, and then we fine-tune it on our end task. So this is the final task of predicting our score distributions, right? So now we have as output the sort of 10-dimensional vector of score distributions that we want to predict. So now I'll just describe some experiments we did to evaluate this method. And so we'll evaluate it on the 3 tasks I've been talking about since the beginning, right? So that's classification, regression to mean to scores, and predicting these score distributions. And the nice thing is that we can do all of this with the same model, because as I said, because the binary labels, because the mean scores are derived from the distribution, once you predict a distribution, you can perform all the other tasks. So this is why I call it a unified prediction model. So here's some quantitative results. This is an ablative analysis, but I won't get into too much detail. Maybe I'll just start off with some of the metrics I'm showing. So the 2 first ones are the KL divergence and the cumulative distribution loss. So these really are measuring how well are you predicting your distributions, right? So these are measures of distance between your predicted and your target distribution. So the lower the better. The next two, so the next one is the mean squared error. So this is measuring how well you're doing at regressing to the mean score. The lower the better here. And then for the correlation coefficient, this is measuring how correlated are your predicted scores with your ground truth scores. So the higher the better. And then lastly, the accuracy is really your classification accuracy. Okay. So what's interesting to see is that this fine-tuning scheme, basically, of training for different tasks and going increasingly towards your end goal, does help to improve performance for all 3 of the tasks. And then if you compare our methods to state-of-the-art methods, you'll see once again it performs quite well across all tasks. And what's interesting to see is that previous works in this field have tackled either 1 or maybe 2 tasks, but not all 3. So the nice thing about this model is that it can really do all 3 tasks at once. So looking at some qualitative results, what I'm showing you here is the top best high quality images in the AVA data set as rated by the ground truth, and the bottom 4, right? So these are the images that are the best and the worst in the data set as rated, in the test set, as rated by users. And then you can see the distributions that have been predicted compared to the ground truth. So the ground truth are the black curves, and the green are their predicted ones. So you can see that it's not doing too badly, but you can see also that there does tend to be, so the predicted distributions tend to almost follow like a template. So you can see that the model is sort of learning almost templates of distributions that are appropriate for a given type of image. So where does it not do so well? As you would imagine, it tends to fail for images that are really on the extremes of the rating scale. So you can see when you have ground truth distributions that are quite skewed, the predictions don't do as well, right? Because the predictions are really kind of have this bias towards less skewed data, which makes sense because the data set itself has a bias towards this type of data. So what we wanted to understand as well is not just is this image good or bad, or how would you rate this image, but also why, right? So we'd like to understand a bit what the model is learning. So there have been a lot of works in computer vision and other fields that have tried to add some interpretability to deep models. So one thing that people have tried very often is to sort of look at the weights that are learned in a deep model, particularly the ones that are a bit earlier on in the pipeline. But this is a bit low level for our task because semantics are a fairly kind of abstract concept. So this doesn't tend to work too well. What we try to do is take an approach similar to GradCam, where what we want to do is understand if we wanted to make an image better or worse, which parts of the image would we have to modify to do that, right? So this is something that's been applied before. So in our case, we took a similar approach. And we tried to basically make the scores worse or better by applying certain gradients. And then we checked to see, okay, which parts of the image would be most affected. So if you do that, so here I'm showing you some qualitative results showing a few examples of that. So you can see like an image, and then you can see the heat map corresponding to with higher emphasis on the regions of the image that are most modified. And so you can see that the image tends to, the model tends to focus on either sort of very semantically meaningful structures, so things like faces, horses, faces, people, and then also foreground objects, things that are quite sharp. So this is also quite likely due to the model itself, which has a strong semantic bias, right? So it's very much tuned towards semantic content by design. So one last thing I wanted to discuss is some recent work that goes beyond predicting aesthetic properties into how can we generate images with certain aesthetic properties that we would like. So there's been quite a lot of recent work on generative image models in general, and then also on how do we condition them to enforce certain properties, right? So very often we might want to condition on categorical variables. So you might want to say, not just sort of, I don't want to necessarily sample an image, just any image, but I would like to sample an image that conforms to a specific category. So for example, I'd like to have an image of a cat, or yeah, something else. Also recently there's been work on, like conditioning generation given a human pose. So let's say, for example, you're inputting an image of a person with a specific stance, and you'd say, okay, I'd like to have this person with a different pose, so I'd like to have their hands in a different position. You can sort of input that as auxiliary, as conditioning information, then also output an image that conforms to that. Another example is semantic layout. So let's say, so maybe some of you have seen some recent work by NVIDIA that does this, where you kind of given as input semantic layouts of a scene, and then what the network is supposed to output to you is sort of like a photorealistic image that conforms to that semantic layout, okay? So in this work, what we'd like to do is to propose a GAN that for photographic fine art. So this is a GAN that's conditioned on not just semantic information, but also aesthetic properties that we might like of an image. And in order to do that, so we condition on semantics in the typical way, using sort of categorical variables. But then we condition on aesthetics, using the score distributions that I've been talking about, right? So using sort of like this normalized score histogram as conditioning information. So I'm just going to go briefly through the architecture. So both the discriminator and the generator follow a typical ResNet pipeline. So you have these kinds of residual blocks that you stack on top of each other to generate to give you your network. So looking into one of these blocks, one of these residual blocks, it's fairly typical. The only kind of particularity here is that rather than using a typical batch normalization layer, we're using what we call a mixed conditional batch normalization layer. And I'll discuss what that is in a few seconds. So given this type of block, as I mentioned, you kind of stack them on top of each other to give you a generator. And you use a kind of similar architecture for the discriminator, except that rather than have residual blocks that are upsampling in the case of the generator, you're downsampling in the case of the discriminator, okay? And so for the discriminator, the way that the conditioning information is introduced is what you see here, right? So you have your input image. You have this set of layers that gives you some sort of image representation here. And then you compute a compatibility function between your image representation with the dot product and some embedding of your conditioning information. So in the case of, if you have semantic information, you have this usually have like a one-hot vector, which you use to select an embedding. And then you compute the dot product between your class, basically your class information, and the image representation. And you can do exactly the same thing for your aesthetic information, right? You can compute a compatibility function between the aesthetic variable, right, which is a score distribution, and your image representation. And you can add all this into to give you your score, your compatibility score between your image and the conditions that you want to hold, right? So this is quite similar, in fact, this was inspired by this work by Miyato and Koyama on projection discriminators. So that's it for the discriminator. So looking a bit deeper into the generator, how do we condition the generator? So as I mentioned, we used what we call a mixed conditional batch normalization layer. So I guess many of you are familiar with batch normalization layers, so this will be familiar to you. So this is really particular to convolutional layers, right? So we're not looking at fully connected layers. So in this case, you have an output of your convolutional network of layer for a given channel. So you're looking at one feature map, and you're looking at one spatial location I, right? So you have one spatial location in one channel. Then you normalize it using the statistics for that channel, right? So you have your mean of the channel C and your sigma. And then you're scaling and shifting using these parameters lambda and beta, right? So you can see that lambda and beta are dependent on the channel. So there's one of these per channel. But then they're also dependent on the aesthetic and semantic properties you want to enforce. So how does that happen? So if you take all these lambdas, so you have, as I mentioned, one lambda per channel. If you stack them into a vector, you have this vector that's with C elements, where C is your number of channels. And you compute this using affine transformations. So basically you say, okay, for every semantic category, I have two affine transformations associated with them. One of which gives me the lambda parameters, and then one affine transformation here that gives me the beta parameters, okay? And then you can see here that basically what you're doing is you're really transforming your aesthetic information. So this is really your score histogram, and you're applying this affine transformation to give you your lambda and your beta parameters, okay? So this is both, this is sort of like a mix of two related batch normalization techniques. So there's one that's called conditional batch normalization, and another one called conditional instance normalization. So it's kind of like a mix of both. So that's the architecture. Now, how do we train it? As you would expect, we use the same AVA data set that I described. To get the aesthetic conditioning information, as I mentioned, we use these histograms. How do we condition on semantics? So as I've been telling you, we don't really have very good semantic labels. So I did what, as I mentioned, people in the past have done, which is try to use a kind of clustering technique to give you sort of pseudo labels, right? So I won't go into the details of the clustering, but you can see that we were able to get, with a specific clustering technique, about 11 categories that are fairly semantically coherent, but unfortunately it's not very large scale, so we had to discard a lot of images which didn't really fit into these categories. Yeah, but you can see that they're fairly semantically coherent, although not entirely. There are still false positives there. So here I'm showing you some generated samples that are kind of fairly successful. So if you look at categories like lake or meadow, sunset, beach, categories like this, these are images that have been conditioned on sort of to be high quality, let's say. And you can see that it does tend to capture fairly recognizable properties of high quality images in these categories. So for example, for the lake category, you see that it tends to capture properties like reflection of water. It also tends to capture some kinds of compositional information. So for example, putting objects like trees off center, having fairly high dynamic range type of properties, a lot of image saturation, color saturation, properties like this. If you condition the image to be low quality, you tend to get things like this. So you can see, for example, for trees that it looks a bit cluttered, the images, the colors are very, very different, the color distributions as well. So here are some ones that were not so successful. So the model tends to not do really well for categories with a lot of structure, so especially things with faces like birds, cats, and portraits. It doesn't do so well. So these are images supposed to be high quality. And then you also see there's a bit of mode collapse as well. So this might also be due to dataset bias, not many samples, and then also just the inherent difficulty of the category. And then you see similar issues here. So this is, for example, these are supposed to be low quality, but it's kind of a mix. And then you can see that, for example, in the bird category, it does tend to capture the fact that if there's a lot of clutter, a lot of branches in the way, it's not very nice. But then beyond that, it doesn't get a lot of structure. So now I'll sum up the talk with a global summary. So we started off by asking the question, can we really take data-driven approaches to these types of tasks, right? Can we really solve subjective appreciation tasks using data-driven approaches? And the answer is yes, if you have large enough scale data sets, as I mentioned, not just in terms of images, but also in terms of the annotations themselves, and then if you have powerful enough representations. So the major challenge in this work, as I've been mentioning many times, is the bias in the data set, which is really hard to address in several ways, right? So most images tend to be average quality. You don't really have many images that are really good or really bad. Another one is that content, the semantic content tends to be biased. So as I showed you in the plot, looking at the tags, very often, you have like many images for nature, landscape, but then very few for these sort of long tail of categories. And then also the raters themselves, right? So the annotators are self-selected. They're in a community of very highly skilled photographers. So their views on what makes an image good or bad is not going to be the same as the average person. And that's it. Thank you.
Is there any question?
Thank you for your talk, very interesting. I just have one question about your last comment. What do you think will happen, and I don't believe you mentioned, when you have scores distribution that are bimodal or multimodal? For instance, you have a population of scorers that are professionals and amateurs, or even when we talk about movies, you have the critics and the average population, and you have bimodal distributions of scores. How do you think it will?
So you mean, what do I mean in terms of what, generation or prediction?
For the prediction, for instance.
So this is why we try not to have like a derivative annotation, right? If you try to compute a mean score for like a bimodal distribution, then you're going to completely erase that information, right? Which is why we really think that the interesting problem to solve is really the distribution problem, where you capture it because that's exactly what you're trying to predict, right? So the bimodality will be preserved in the prediction that you make. And then this is something that you can use to inform you about the property of this image, that this is somewhat controversial in some way, or there's something interesting going on in this image.
Thank you for the specifically the prediction problem. So, do you have a ballpark figure for how much time it took to train your models, your final models?
So that's really tricky, right? Because it depends on so many things. It depends on the hardware you use. So I can tell you that if you have I think I trained this stuff with like maybe 4 P100 GPUs, and it took I think like maybe 18 hours or something like that. So it's not crazy.
Okay,
it's not like ImageNet, because there's 250K images, and it's very hard to do augmentation with this type of work, which means that your data set is really sort of limited, because it's hard to do things like you can't really jitter the colors in the image because that really affects the aesthetic properties. So it's really hard to kind of augment your data set, and that way it tends to converge very quickly. It doesn't really have much to gain by training more.
Yeah. Okay. Thank you very much.
Another question? No, one question from me. We have 1 minute left. Okay. Would it be possible to use your framework for optimizing an image? For instance, if I authorize cropping or contrast change or something like that?
So the way it is now, no. So in the first image, when we tried to do this sort of interpretability analysis, we did try to do that, right? So we said, okay, we have an image that has a specific score. If we wanted to make the score higher, how can we modify the image? How would we change the gradients? But that doesn't work. It doesn't give you anything appreciable in the image itself, right? It tends to basically destroy the image. So you need to have a lot of constraints, not on the structure of the image and things like that, to preserve the image structure. And for the generative parts, also, it's the way we generate images, we don't start off with an input image. So we can't really do like an enhancement technique. We can sort of just do like a conditional generation thing. But I mean, I can definitely imagine having like a kind of enhancement model where you input an image, you condition it on some properties, and then you expect the image to be modified with the conditions that you put in. But that's not something that what I do can handle, yeah. But there have been works that have done it. There have been like image enhancement works that try to do that sort of thing.
Thank you again.